Nuclear notes, page 9. So what we're going to look at is the half-life of radioactive isotopes. You need to dig back into your earth science days because you guys did do half-life and half-life calculations. So let's do a quick reminder here. Half-life, it is the amount of time it takes for half of the atoms in a given sample to decay. That means that half of the atoms present in that specific amount of time, they go from being unstable to stable or more stable. The half-life for selected radioisotopes are listed on table N. The half-life, the amount of time per cycle, is always the same. It never changes. Okay? It cannot be altered by pressure, temperature, or chemical combinations. We're going to cross this off because this is no longer on your reference tables, and we're just going to use a simple manipulation of how to solve half-life problems. One of the things I wanted to show you is that the half-life graph for any sample will always look exactly the same. The original mass, no half-life cycles have occurred. No matter what the original mass is, by the time you get to the first half-life cycle, that number is cut in half. And then when you get to the second half-life cycle, that number is cut in half again. And when you get to the third half-life cycle, the number is cut again, and this continues on. So if I was to assign fractions or percentages, here, the percentage of my sample that's radioactive would be 1 over 1, or 100%. At the end of my first cycle, now only 1/2 of my original sample remains radioactive, or 50%. These values never change. At the end of my second half-life cycle, well, I've gone from 50% to now only 25% remains radioactive, or now 1/4 of the original sample is still radioactive. Okay, and I'll go to one more. At the end of the third half-life cycle, okay, only 1/8 of the original sample is still radioactive, which means that is what, around 12.5%. So no matter the identity of the radioisotope, no matter the original mass, the graph always will look like this, and the fractions and the percentage always match up to the exact same half-life cycle number. Here in the video, I will go through one example of how to solve these, and then we will do some more in class. So the half-life of nitrogen-16 is 7.2 seconds. How much of a 100 microgram sample of the N16 will remain after 28.8 seconds? So this 7.2 seconds is the amount of time per cycle. 28.8 seconds represents the total time passed. Okay? So I just want to look at the number of half-life cycles. Well, you have your 0 cycles, 1 cycle, 2 cycle, 3 cycle, 4 cycle. I'm just going to list those. And you know what? The fraction remaining, if no half-lives, my fraction is 1 over 1. That never changes. At the end of the first cycle, now it's 1/2. End of the second cycle, it's 1/4. At the end of the third cycle, 1/8. And at the end of the fourth cycle, it's 1/16. This fraction always matches up to this specific half-life or cycle that has passed. If 0 cycles have passed, 0 time has passed. Okay? For nitrogen-16 to go from 0 to 7, it requires 7.2 seconds. So 7.2 seconds have passed one cycle. Now it's an additional, to go from cycle 1 to cycle 2, it's an additional 7.2 seconds. So now, when I get to the end of the cycle, the amount of time that has passed would be 14.4 seconds. I'm going to just move this a little bit, okay? To go from the second cycle to the third cycle, it requires another 7.2 seconds. So that means the total time that has passed, I have to add another 7.2 seconds to the number before it. So that is 6, and 14 and 7 is 21. So now, by the time nitrogen 16 reaches its third cycle, 21.6 seconds have passed. To go from the third cycle to the fourth cycle, it requires another 7.2 seconds to pass by. So now the total time is, I have to add 7.2 to the 21.6. So that gives me 2 plus the 0.6 is 8, and 21 plus 7 is 28 seconds. So this is the total time. So that means for our sample of nitrogen 16, after 28.8 seconds have passed, that means 4 half-life cycles have occurred. That means 1/16 of the original mass. So here is the original mass remains. So you could do some simple math, or you could do it right here. So the original mass is 100, because that's what we start with, and filling in the chart. Well, at the end, 1/2 of 100 happens to be 50, and we're using the micrograms, so I guess I should put in symbols. And then by the time you go from the first cycle to the second cycle, this mass cuts in half again, so we're at 25 micrograms. By the time we go from the second cycle to the third cycle, now the mass is cut in half again, so that would be 12.5 micrograms. And then it needs to go through one more cycle, so this mass is cut in half again, so then we're at 6.25 micrograms. So nitrogen 16, when it passes through 8.8 seconds, only 6.25 micrograms of its original 100-gram sample is still radioactive. We will do more half-life practice problems in class, but this is the basic pattern of how to fill it out and think through the process.